Welcome to Mathematical Analysis. Today we are diving into one of the most fascinating and powerful ideas in the study of infinite series, absolute convergence. If you have ever wondered how we can safely add an infinite list of numbers that flip between positive and negative without the sum spiraling out of control, you are in the right place. We will build this concept from the ground up, ensuring you truly understand not just the mechanics, but the deep intuition behind it. Let us get started. To understand absolute convergence, imagine you are taking a journey along a straight path. You take some steps forward and some steps backward. If you eventually settle at a specific final location, your journey converges. But what if we apply a much stricter rule? Imagine we magically turn every single backward step into a forward step. We are now looking at the total amount of energy you spent walking, regardless of direction. If this total energy is still a finite number, meaning you did not walk forever, your journey is absolutely convergent. It is a much stronger guarantee of predictability. Building on that analogy, let us look at this diagram. On the top axis, you see ordinary convergence. The person takes steps forward and backward, oscillating but eventually settling near a limit labeled L. Now, look at the bottom axis, representing absolute convergence. Here, every single step, whether originally forward or backward, is laid out end to end in the positive direction. We are accumulating the total distance. The thick vertical line on the right represents a finite limit wall. Because the total accumulated distance does not crash through this wall, the series is absolutely convergent. Now that we have a visual intuition, let us translate this into mathematics. In mathematical analysis, we deal with infinite series, which are endless lists of numbers added together. A series converges absolutely if the series formed by taking the absolute value of every single term also adds up to a finite number. Look at the formula on screen. The symbol a sub n represents the individual terms of our original series, which can be positive or negative. The vertical bars represent the absolute value operation, forcing every term to be positive. The summation symbol tells us to add all these infinitely many positive terms together. If this sum is finite, the original series is absolutely convergent. This strict definition leads us to one of the most important guarantees in all of calculus and analysis. It is a usable theorem stating that if a series converges absolutely, then the original mixed sign series must also converge in the ordinary sense. Think of it like a budget. If you can afford to pay for everything, even when you are charged for both your deposits and your withdrawals, you can definitely balance your normal checkbook. We can actually prove this mathematically using a clever trick by comparing the original terms to their absolute values. Let us look at the mathematical foundation of its proof. The formula on screen shows a new expression created by adding the original term a sub n to its absolute value. If a sub n is negative, this sum is exactly 0. If a sub n is positive, this sum is exactly twice the absolute value. Therefore, this combination is always bounded between 0 and 2 times the absolute value. This perfect upper boundary is the key to proving our theorem. Now that we have established this bounding formula, let us use it to set up the proof of our theorem. We begin by applying the summation operation to all parts of our inequality, from n equals 1 to infinity. Because we assumed our original series is absolutely convergent, we know for a fact that the infinite sum of the absolute values is a finite number. Multiplying a finite number by 2 still gives a finite number. Now we invoke the comparison test from calculus. This test tells us that a series smaller than a known convergent series must also converge. Since our combined expression is bounded above by this convergent series, the sum of a sub n plus its absolute value must also converge to a finite value. Our all positive series is perfectly well behaved. Continuing from our convergent sum, we are ready to derive the final result of our theorem. We use a simple algebraic rearrangement to isolate our original term a sub n. We express it as the difference between our combined expression and the absolute value. This step is crucial because it breaks the original series into two separate parts that we already understand perfectly. Finally, we apply the summation operation to both sides of our rearranged equation. Since we just proved that the first sum on the right side converges, and we already knew the second sum converges by our initial assumption, their difference must also be a finite number. Subtracting one finite number from another finite number always yields a finite result. Therefore, the original series converges, proving that absolute convergence strictly implies ordinary convergence. So we have proven that absolute convergence guarantees ordinary convergence. This brings us to a crucial connection with the convergence tests you learned earlier. When you apply the ratio test or the root test to a series with mixed signs, you are instructed to put absolute value bars around the terms before taking the limit. Because you are forcing the terms to be positive before testing them, these tests are actually testing for absolute convergence, not just ordinary convergence. If a series passes either of these tests, it is absolutely convergent and therefore ordinary convergent too. Before we move on, let us see this with a concrete example. We will look at the alternating geometric series to see how absolute convergence works in practice. The formula on screen defines the general term of our series. The numerator, -1 to the power of n, is responsible for the alternating signs. It makes the terms negative when n is odd and positive when n is even. The denominator, 2 to the power of n, makes the fractions get smaller and smaller as n increases. Our strategy will be to strip away the alternating negative signs and analyze the resulting positive series. Let us work through the steps. We want to determine if this alternating series is absolutely convergent. To test for this, we apply the absolute value operation to the entire general term. The absolute value destroys the negative signs completely. This means the alternating part in the numerator simply becomes a positive one. The denominator is already positive, so it remains unchanged. We are now left with a new simplified term that is always positive, 1 over 2 to the power of n. This term represents the absolute distance of each step in our series. Continuing with our simplified positive term, we must now determine if its infinite sum converges. This is a standard geometric series, where each term is found by multiplying the previous one by a fixed fraction, which is a common ratio of 1/2. Because the common ratio is strictly less than 1, we know this series converges to a finite number. Specifically, this infinite sum evaluates exactly to 1. Since the series of absolute values converges to a finite number, we can confidently conclude that the original alternating series is absolutely convergent. Now that we have seen a successful case, let us look at a slightly more complex scenario where absolute convergence fails. We will examine the alternating harmonic series. The formula shown generates the sequence 1, minus 1/2, positive 1/3, minus 1/4, and so on. The terms are steadily shrinking towards 0 as the denominator n grows, while alternating in sign back and forth. Just like before, our approach is to take the absolute value of the terms and see if the resulting positive series adds up to a finite number. Let us apply our test. We place absolute value bars around the general term to test for absolute convergence. Once again, the absolute value operation removes the alternating sign component entirely. This turns the numerator into a constant positive one. The denominator, n, represents the position in the series and is a positive integer, so it stays exactly the same. The resulting term is simply 1 over n. This means the series of absolute values is the standard harmonic series, which is the sum of the reciprocals of all positive integers.
Now we must evaluate if this specific sum is finite or infinite. We know from the integral test or the p-series test that the standard harmonic series diverges to infinity. Even though the terms get smaller, they do not get smaller fast enough to sum to a finite number. Because the sum of the absolute values is infinite, the original alternating harmonic series is not absolutely convergent. It does converge in the ordinary sense, which is called conditional convergence, but it fails this strict absolute test. This distinction is incredibly important.
This brings us to an important question. Why do mathematicians care so much about whether a series converges absolutely or just conditionally? The answer lies in how these series behave when you shuffle their terms around. In everyday arithmetic, the order of addition does not matter. However, for infinite series, this property breaks down entirely unless you have absolute convergence. The famous Riemann rearrangement theorem states that if a series is only conditionally convergent, you can rearrange its terms to make it sum to absolutely any number you want. But an absolutely convergent series is completely immune to this chaos, always summing to the exact same value. Let us summarize what we have learned today. Absolute convergence is the strongest form of convergence for an infinite series, requiring the sum of the absolute values to be finite. We proved that if a series possesses this property, it is guaranteed to converge in the ordinary sense as well. Finally, we learned that absolute convergence protects the series from the bizarre effects of the Riemann rearrangement theorem, ensuring the sum remains perfectly stable no matter how the terms are reordered. You now have a solid foundation in absolute convergence. Great work!